Assalamu alaikum and welcome back. In network performance evaluation studies, we often have to estimate or infer the general characteristics of a system given just some particular observations. This process of induction requires us to take a sample which is representative of the system at large. In many cases, we cannot take an exhaustive sample. This may be due to the system taking, for example, continuous values as inputs. So we cannot test the system for all possible values. Even in other cases, your system may be having too many factors, and it's not possible to try all possible factors. So we take some sample data and we try to infer from that data some general properties of the system. This is in a way analogous to the way opinion polls are done. So for example, you may hear or you may read a report in the newspapers that such and such candidate has 70% chances of winning the forthcoming elections. The question is, how do they actually form this estimate? They actually do not go and ask every person in the entire population for their opinion, because that may be very cost prohibitive. And so taking a census when we take opinions from everyone is in many cases out of question. What we are left to is the option of taking a representative sample and then asking their opinion. And if this sample is a good representation of the system at large, we can actually form very good opinions about the population from just this sample. This information that the candidate has 70% chances of winning the election is in itself meaningless, because it has to be quantified with the amount of certainty or confidence that we have that we would be actually close to this value. And also we need to have a margin of error, because all measurements have some errors associated. So we need to be very careful with this. And when we're talking of network performance evaluation studies, we should be very careful when we are reporting performance of a system as saying that it performs and its value for this parameter is this. We cannot state that until we have done the calculations for the entire population. If we're just doing a simulation in which we are having some observations, we should be very careful to quantify the confidence that we have in our measurements and also the margin of error. This session is actually going to talk about all these things which are relevant to sampling. So the first topic I want to talk about is what is sampling, how to get representative samples, what are the problems of bias and how they can corrupt the usefulness of results. We will also talk about the sampling distribution, which is the theoretical basis of sampling. When we make a statement like so and so has the chances of, let's say, 70% with a margin of error of this and this, so this actually has a statistical background, and we can give guarantees that this will happen with so much confidence. So we'll be studying the theoretical underpinnings which actually help us predict or estimate with confidence. Lastly, I'm going to talk about the concept of estimating from a single sample, because in many scientific studies, we only have a single sample and we want to estimate the parameters of the entire population on the basis of that. It must be remembered and noted very carefully that a sample is basically a random selection, and therefore every time you take a sample, it is not going to be the same unless you're taking the same sample again. But the question again is, we need to have a sample which is representative of the population. So every sample that we take is going to have some random error, that the results are not going to be the same. So when we are extrapolating results from a single sample, we need to quantify our confidence that if someone was to do this sample again, would they have similar results or completely different results? So this is a very practical problem, and we'd be discussing this in this section. We start with sampling basics. So the first thing I want to talk about is some terminology. What is a population and what is a sample? So a population is the entire set of items that we are interested in. So this population may be a population of human beings. In the example cited of opinion polls, we can imagine the entire population of Pakistan being our population of interest. And the sample would be the 1,000 or 2,000 people that we ask for their opinion. So in all cases, we don't have a population of humans only. So whatever thing we're interested in, जब हम उसकी complete sense में उसकी बात करें, so that would be the population, and the particular measurements or the subset of the entire set that we are working on would be called the sample. So this is an important concept which must be very clear, that it's not necessary when we talk of population that it only deals with humans. We can imagine a system, and we've seen the slide before, so we can imagine a method of doing things, and the population here would be how that system responds in the long-term case. So we would have a probability density function, and we would have a mean value. Imagine that the probability density function of the system you're studying is centered at mu A. So this would be the entire population, जो आपकी पूरी density curve describe कर रहा है. But when we are actually working on this system, you only have some samples from it. तो जितना data आपको मिल रहा है, that would be the sample, and that sample you would like to be representative of the entire population, which is represented by the density curve. Another important point here is we often assume that the sample is taken, the individual observations are independent from each other. This is a very strong assumption which is often made. So we must be very careful that our system actually satisfies this, because in many cases the lack of independence can create bias. So let me talk of some parameters in statistics. The definition of a parameter is a measurement that is done on the entire population. So if we talk of the proportion of people who are going to vote in a certain way in the entire population, then this is a parameter. If we talk of a population of some variable which is taking numbers, you can take the mean of it. तो जब हम पूरी population की बात कर रहे हैं, that is a parameter. So the whole population mean is a parameter. You can also talk of the population standard deviation, and this then would apply to the entire population. जब हम अपने sample की बात करें, तो उसमें उन जो calculation हम उस पर करते हैं, उसको हम parameter नहीं कहते, उसको हम statistic कहते हैं. These statistics are actually calculated on samples. Some examples would be the sample mean, in which we are taking the mean of all the observation in a sample. We can also talk of the sample standard deviation, that in a given sample, for all the observation, what is the standard deviation? Furthermore, we can talk of the sample proportion. It must be emphasized here that all these statistics are actually random variables. What do we mean by it being a random variable? So the idea is that the process of extracting a sample from a population is a random process, because before we have actually extracted the sample, we do not know what sample we'll be getting. Furthermore, if we keep on taking these samples, we'd be getting different samples. So the calculations that we do on these samples would be different as well. In that sense, this is called a random variable. Before the extraction of the sample, we do not know what the value would be. This is in contrast to the parameters, because parameters are fixed values. They are not random variables, so the idea of probability density functions and probability distributions do not apply to them. But sample statistics are random variables, and we can define them in the long-term averages, because like in the case of probability, you can say that, okay, if I take so many samples, infinitely many samples, my sample mean, for example, sample mean is a sample statistic. So I'm taking as an example of a sample statistic, sample mean. I can say that the sample mean is going to be distributed in some way. Or I can make other statements in a probabilistic sense. We can talk of distributions. So it is very important that each sample would present a different statistic, and therefore we say that the sample statistic is a random variable which can be described by a probability distribution. Okay, so an important aspect of using statistics and the prime aim of using sampling in the first place is that we want to estimate parameters of the population. We do not know, जो example cite किया गया था opinion poll का, we do not know that what percentage of the entire population is going to vote for candidate A. But what we can do is we can take a poll of a smaller sample, and if that sample is representative of the whole population, we can make inferences on the base of this. So the point here is that we actually use statistics for estimating parameters. This is very important. So what kind of estimations can we do? We can use sample statistics as point estimators. So we can, for example, use X bar as an estimator of mu, where X bar is the sample mean, and we use it to estimate the true population mean. We do not know the true population mean, but given X bar, we can actually estimate what the true population mean would be like. So this is an example of a point estimator, because we are giving just one value, and we are not describing the margin of error, or we are not describing an interval around this point estimator in which we can say that, okay, the true parameter would be within this range of the point estimator. If we actually do that we do not just provide a point as an estimator, but in fact an interval, then we have what is known as the interval estimator, also known as confidence intervals. When we're using confidence intervals, we give two information along with confidence intervals. One thing is how confident we are that a given interval would contain the true population parameter, and the second thing is the margin of error. That, okay, if I've stated that 79% of the people are going to vote for candidate A on the basis of my sample, this statement on its own is not meaningful until I specify the margin of error and also the confidence level which I'm using for that. So we'd be seeing this in this lecture. A statement which would include a confidence interval would be something like this, that I am 95% confident that 79% plus minus 3 would contain the true population proportion of people who would be voting for candidate A. So the next question that we should answer now is that how do we actually choose a sample? So we know samples are very important. They are even indispensable because in many cases. So the next question that we should answer now is that how do we actually choose a sample? So we know samples are very important. They are even indispensable because in many cases taking a census or doing entire calculations on the population is not possible. So in that case, we need to sample. The question is, how do we ensure that our sample is representative of the entire population? What we want to do is, we want to have an unbiased sample. और इसको हम further explain करेंगे कि if you have a systematic bias, your sample would actually keep on indicating an estimate which is away from the true parameter that we are estimating. So this is actually shown in the slide here, the questions of what is bias and what is variability. So you can imagine trying to hit dots on a board and you're trying to hit the bullseye. So if you have lots of randomness and you have some systematic bias as well, as shown on the left top side, you would see that most of the arrows would be falling away from the center, and also they have lots of variability. So we would say that you have high systematic bias and also high variability. Why do we have bias and why do we have variability? The answer to that is, bias is because of problems in the way sampling was done. So if you have a process of creating sample which is not going to be representative of the system, you would have some systematic bias, which is actually very bad when we're doing sampling. We want to remove all bias. उसके अलावा कुछ random variation भी है. As seen in the left top graph, most of the arrows are actually centered around some point, but they also have lots of variance. This variance can be removed if we take lots of samples. अगर हमारा sample size बड़ा है, अगर हम sample में let's say 200 observations की average ले रहे हैं तो उसमें variation कम होगी. अगर हमारा sample size छोटा है तो उसमें variation ज़्यादा होगी. So what we desire is what is shown on the bottom right side. We want low bias and low variability. इसको अचीव करने के लिए हमारा सैम्पलिंग मेथड भी अच्छा होना चाहिए जिसमें सारे बायस को हम रिमूव कर रहे हैं as much as possible. And also we have sample size which is large enough to ensure that there is low variability. And you have other cases as well, but where we want to be is the bottom right side, low bias and low variability. We can tolerate variability because even if you have high variability, as shown on the left bottom graph, you see that still it is centered around the true parameter. But when we have systematic bias, the estimates we're going to form from our sample are going to be misleading, and that can be very problematic. A spectacular case in which the sampling process went very wrong was the 1936 elections in the US, in which there was a magazine known as Literary Digest. They perhaps made the biggest poll ever done. So this was a very ambitious poll. They actually sent questionnaires to 10 million people, and that is in the current sense of polling, this is a huge poll. So if you are actually asking 10 million people for their opinion, chances, intuition would say that the chances are good that you would have a representative sample of the population because you're asking a lot of people. And this election was contested by two candidates, the incumbent President Roosevelt and also Alf Landon, who was the competitor. So Literary Digest actually predicted a landslide victory for Alf Landon. The number of people they polled was 10 million, and the replies they received was 2.3 million, which is 23% response rate. But the results actually went spectacularly wrong. It actually was a landslide victory for President Roosevelt. Or in the meanwhile, there was another guy, George Gallup, who had made a very small sample compared to the sample of Literary Digest. There's 50,000 people. And not only George Gallup was able to predict the victory for President Roosevelt, they also predicted that the Literary Digest sample or the poll is going to be wrong for this and this reason. And that was indeed the case. The reason for this mishap, as if we consider it from the perspective of Literary Digest, was that their poll was unrepresentative, or it had a bias, because the method in which they were selecting the people was biased. It was done on the basis of membership of their magazine and on the basis of telephone numbers. So in those times, not many people had telephone numbers. So you were consistently ruling out a part of the population which was actually a major part of the population. So for that reason, their analysis was misleading because it had a systematic bias. On the other hand, George Gallup's company made every effort to ensure that the sample they have, it has an equal chance for everyone to come in. So it is representative of the population at large. This actually convinced the polling industry to not focus on having very large samples, but having samples in which bias is removed, because you can do a lot with small samples as long as the bias is removed, as we shall see, which holds true for network performance evaluation studies as well. You don't need a very large sample, but the sample has to be built in a careful sense where you remove all biases, and the assumption that we have should also be fulfilled, especially the assumption of independence, because dependence amongst the observation would create an obvious bias. So let me now discuss the different kinds of samples that we can have, or we usually have. The first kind is known as a probability sample. In a probability sample, the entire population, every item, every unit in the entire population has some non-zero probability of being in the sample. इसकी एक पर्टिकुलर जो कैटेगरी है उसको हम कहते हैं सिंपल रैंडम सैम्पलिंग, या उसको हम SRS एब्रीविएट करके कहते हैं. उसके अंदर if we are taking a sample of size 500, then all possible subsets of the population of size 500 have an equal chance of being selected. There is another kind of probability sampling which is known as stratified sampling. इसमें हम ये करते हैं कि we divide the entire population into subpopulations और उनको हम stratas कहते हैं, with the assumption that these stratas are quite different from each other. और उसके बाद उन stratas में से हम probabilistically selections करते हैं. So we can imagine that if we want to make some estimate about a population of all IP packets, हम उसको TCP और UDP stratas में divide कर सकते हैं और उसके अंदर से हम rule define करके selections कर सकते हैं. Another kind of sampling technique is what is known as systematic sampling. In this, you order in some way, you order all of the packets in some enumerative sense, और उसके बाद आप कह सकते हैं कि okay, I'm going to pick the kth item. After every kth item, I'm going to pick up the item and place it in the sample. And this is often done in networking systems and done by some major vendors. Also, another common type, which may not be very good way of doing sampling, is what is known as a convenience sample, in which you do not actually go out of your way to ensure total randomness. You actually pick up those items which are convenient to you. This is very common in social sciences. For our work, we have to ensure that whatever method we use, it has to be representative of the population at large, and the best bet for doing that is to do a random sample. Simple random sampling is actually a good way of achieving representative samples. Let us now talk about sampling distribution. We've already seen that sample statistics can be thought of as random variables. So if it is a random variable, then it would have a probability distribution as well. So the probability distribution of a sample statistic is its sampling distribution. इसकी intuition ये है कि हम जब बार बार sample करेंगे और वो statistic calculate करेंगे, we're not going to get the same value because it's a random variable. It is going to take a range of values, but it may be that it is more prone to taking certain values and less likely to take other values, and that actually dictates what the shape of the distribution would be. So this is the sampling distribution, and this is a very fundamental concept in inferential statistics. So today I'm going to focus on just the sample mean. There are other kinds of sample statistics. For example, we may calculate the sample median, or we may calculate the sample standard deviation, or other parameters, sample proportion. Today I'm going to focus, for the sake of simplicity, only on sample mean. So let's see what a sample would be like if we're drawing a sample from a population, and what the sampling distribution of sample mean would be like. So as shown in the slide, you have a population, and the population is quite large. It has a mean of mu and standard deviation of sigma. So please remember the convention that when we're talking of parameters, they're usually in Greek letters. Jis tarah is case mein you have mu for the population mean, and you have sigma for the population standard deviation. The concept I'm trying to convey is that when we take a sample from this, and it is shown in the slide as SRS of size n, where size n is indicating the size of your sample, कि आप एक sample में कितने लोगों के ऊपर measurement कर रहे हैं. So as mentioned, your population may be a population of people, it may also be a population of times or whatever. So if it is a continuous variable, you can think of or if it's measured on interval ratio scales, you can measure it as a mean as well. So when we take a sample from this population and we calculate the sample mean, we're going to get different x bars. और x bar Roman letter है, and this is telling us the mean of one particular sample. Okay, so we're going to get different x bars. If we draw this, the distribution of this x bar, we are going to get what is known as the sampling distribution, and that is shown on the right hand side of the slide shown. You can see that the sampling distribution of the mean actually follows the familiar bell-shaped curve. Yani ke the sampling distribution has a normal distribution and it is centered at mu, which is very interesting because that is what we want. We want our sample means to be centered at the true population mean. इसके अलावा आप देख सकते हैं कि sampling distribution of the mean has a standard deviation, and that standard deviation also known as standard error. Please remember this is very important. So the sample error is shown in the figure, and it is equal to sigma over under root of n when we are talking of the sample mean. दूसरे statistics की बात करेंगे तो उनके standard errors फर्क होंगे, but for the sample mean the standard error is sigma over under root of n. Sigma here is the population's standard deviation, or n is the size of the sample. So we can see that the probability density function has the familiar bell-shaped curve, और इसका मतलब ये है कि if we are to take infinite number of samples और x bar को हम replot करते रहें, तो approximately you would have a graph like this which has the normal bell-shaped curve. उसके अलावा we know that for a normal distribution that is centered at mu, उसकी expected value mu है. So in that sense, the long-term average of the sampling distribution is mu, which is good for us. इसका मतलब ये है कि if you take a lot of samples, so you are going to be very close to mu, which is what we want. Sample mean को हम इस्तेमाल करते हैं as estimator of the true population mean. Standard error I've already mentioned is sigma over under root of n, और हम आज के सेशन में देखेंगे कि as we increase n, which means the size of your sample, n अगर हम 10 observations का sample ले रहे हैं तो n would be 10. अगर हम 20 observations का sample ले रहे हैं तो n would be 20. If you keep on increasing n, अपना sample आप ज़्यादा large करेंगे तो standard error भी कम हो जाएगा. So let me give you the intuition of standard error. Standard error का मतलब ये है कि because we are doing sampling, it is likely that we are not going to hit on the exact parameter that we want. But how likely is it? उसको हम standard error से measure करते हैं कि this is the standard error of estimation when we are doing sampling. So why do we actually get this bell-shaped curve? तो उसके लिए I'll be covering this in just a while. Before that, I want to talk a little about the normal distribution, because normal distribution is a theoretical distribution, and we don't have actually data that correspond to this, क्योंकि इसमें even very extreme values have non-zero probabilities. So what you often have is a close approximation. तो उसके अलावा हम exact fit तो इसका नहीं होगा, but if it is close enough, then we can say that okay, we can apply all the methods that apply to the normal distribution. Normal distribution की एक बड़ी important property है कि it has two parameters, and if we know those two parameters, we can predict a lot about data. So वो दो parameters क्या हैं? वो parameters हैं the mean of the normal distribution and the standard deviation. So knowing these, you can actually predict how much of data is going to lie in what range. As an example, you can state that 68% of your data is going to be within plus minus 1 standard deviation of the mean. You can also say that approximately 95% of your data is going to be within 2 standard deviations of the mean. Furthermore, you can also say that within 3 plus minus standard deviations, you would be approximately having 99.7% of all your data values. This is also known as the empirical rule. And this is very important to understand. In the context of sampling, this would mean कि आपके ज़्यादातर sample means जो हैं, वो कुछ standard deviations के अंदर ही lie करेंगे from the mean. And it is going to be very rare that you take a sample और जो आप estimator इस्तेमाल करें, that's way off from the true population parameter. So because of that, that gives us confidence. Theoretically हमें backing मिल रही है कि okay, what we are doing is actually sound. Now we come to the point that why do we have the sampling distribution in the form of a bell-shaped curve और उसका जो center है वो mu है. This is very desirable, but we want to know why this is the case. This is the case because of two mathematical principles. The first one is the central limit theorem, which helps us obtain the bell-shaped curve. And the second one is the law of large numbers, which helps us to ensure that this normal distribution is centered on mu, the true population parameter. So a few words about the central limit theorem. Central limit theorem में ये होता है कि if you have n independent random variables, and if this n is large and you take a sum of all these random variables, the sum itself would be a random variable which has a normal distribution. इस केस में हम sum तो नहीं ले रहे, लेकिन हम sample लेते हैं. Let's say we take a sample of n individuals and we take measurements on them and we take an average. An average is just a sum divided by some value. So it is a normalized sum. इस वजह से जो हमारी sampling distribution बनती है of the sample mean, that also has the desirable familiar bell-shaped curve. And this actually becomes true as the number of n increases. Central limit theorem में भी यही है. All your random variables जो कि जिनका sum हो रहा है, they have to be independent, drawn from the same population, having same variance. And even if they don't have the same variance, this is actually the interesting part. Even if the input distributions are not normal, if you keep on adding them for a relatively large value of n, what you would have is a normal distribution. In fact, we'd have a chance to see this. Again, let me reiterate this. Central limit theorem कहता है कि अगर आपके जो input variables हैं, even if they don't subscribe to the normal distribution, अगर हम उनकी average लें और average की हम probability distribution देखें तो वो एक normal distribution में होगा. Law of large numbers actually tells us that if we take a large enough sample and if we average it, the average value would approach the true value for it. हमारे case में if we take a sample which is sufficiently large and if we take the sample mean of it, it is going to converge to the true population mean. I'm going to show you some illustrations to actually make this concept very clear to you. So the first thing I want to show you is some simulations, because ये जो हम बात कर रहे हैं ये एक theoretical बात है. We cannot do infinite number of samples. In fact, we only do typically one sample. But if we were to take infinite sample, तब ये आपके पास normal distribution आती है. लेकिन we can simulate taking many samples. जो मैं आपको example दिखा रहा हूँ उसमें I'm taking 4,000 samples. And I'm going to show you a histogram of the values taken by sample means, and we are going to see that is it really true that irrespective of the parent population, your sample mean is going to look like a normal curve. तो इसको हम देखते हैं. The first thing I'm going to show you is the uniform population distribution. So uniform population distribution का मतलब है almost everything is equally likely. उसके अंदर से मैं 4,000 samples extract करता हूँ, each having a size of 30 items or 30 observations. And if I take the sample mean of it and if I plot it and I do it for all 4,000 instances, the result I'm going to get is shown in the bottom left side of this slide. As you can see, we have what is known as a normal curve, and it is centered at approximately 5, which is the true population mean for the parent population, which actually shows us central limit theorem की वजह से हालांकि आपकी parent population uniformly distributed थी, लेकिन when we take sample means of it and we keep on doing it for 4,000 times और उसका histogram आप देख रहे हैं कि this is normally distributed. So we see that this is true for uniform distribution. Let's see the case for normal distribution. We do the same thing, 4,000 samples, each sample has 30 observations. We take sample means and plot it. So we observe again that most of the sample means are actually very close to the true population mean. और आपकी जो distribution बन रही है histogram की, वो एक normal distribution है. Let's see the same for a skewed distribution. So interestingly, even for a skewed distribution, when we take enough number of items in a sample and we keep on taking such samples, the histogram that we are going to get is not going to be normally distributed. Lastly, I'm going to show you an extreme example. You have a bimodal population distribution. Isko agar hum, if we take samples from this and if we plot the sample means, we again see that we have a normal distribution. So central limit theorem then has some substance, and we have seen this through simulations. The important thing here is we need to observe that we've taken a sample of size n is equal to 30. If your sample is lesser than this, then central limit theorem may not yet kick in. And because of that, your sampling distribution that you get for, or the sampling histogram that you get for the instances that you actually run this sample for, is not going to be a true normal distribution. It is going to be more spread out. And it is going to have maybe some other distribution. So we need to be very careful that we have samples, we have a sample with enough observations in it if we really want to ensure that the normal distribution assumption is met. Let me now show you through simulations the effect of law of large numbers. मैंने पहले भी इस चीज़ को अभी स्टेट किया कि law of large numbers helps the sampling distribution to be centered at the true population parameter value that we want. इस केस में we see that the parent population has 16,000 items and they are in the first case uniformly distributed. So let us take sample means from this population. We take samples, we take means of it, we plot it. तो आप observe अगर करें तो जो sampling distribution है, it is centered at the true population mean. This is the same for normal distribution, right skewed distribution, and bimodal distribution. So law of large numbers actually helps us ensure that for sufficiently large samples, the sample mean is going to converge to the true population mean. So let me reiterate. Central limit theorem ensure करता है कि sampling distribution bell shaped curve में होगी या उसका normal distribution होगी, और law of large numbers ये ensure करता है कि sampling distribution जो है वो true population parameter पे center होगी. In our case, the true population mean. Now I'm going to use the same simulation set to illustrate another very important idea of the standard error. I've mentioned that the standard error is the standard deviation that you would have due to the process of sampling from the true population mean. So as you can observe, the point I'm trying to make here is that the standard error is inversely proportional to the under root of n. In this case, we are taking 4,000 samples again, and each sample is of size 30. So when we have performed this simulation, what we have confirmed is that this formula of standard error is actually holding true. अगर आप ऊपर जितनी चार population आपको दिखाई हुई हैं उनमें observe करें तो जो उनके standard deviations हैं, नीचे वाली जो graphs हैं उनके अंदर standard deviation उसकी compressed forms हैं, because we are dividing in all cases by the number of samples, number of items in a sample. So n, it's actually a little confusing, but you should understand the difference. n जो है वो एक sample के अंदर कितने item है उसको denote कर रहा है, और samples is equal to 4,000 जो लिखा हुआ है उसका मतलब है कि we're taking 4,000 samples, each having 30 items in it. So we see a close match of the prediction of standard error and empirically observed standard deviation of the sampling distribution. उन दोनों में काफ़ी close match है, which is again a confirmation of the mathematical formula through our simulation. Lastly, I'm going to show you that the sampling error is actually inversely proportional to the size of the number of items in the sample. And this actually makes sense. अगर आपका sample में ज़्यादा items होंगे, ज़्यादा observations होंगी, तो आपका sampling error को कम ही होना चाहिए. और वो इस inverse relationship में भी है कि standard error is equal to the population standard deviation divided by the under root of the number of items in the sample. इस स्लाइड में आप देख सकते हैं कि जो ओरिजिनल पॉपुलेशन है उसकी स्टैंडर्ड डिविएशन 2.882 है. We're interested in seeing how the standard error corresponds to the increase in sample size. So it can actually be seen from the formula because we have small n in the denominator. Increasing the number of items in a sample should reduce the amount of standard error. That is seen from the results of this simulation. In the top right figure, we see that we only have sample of size 2. And even with a sample of size 2, we almost have a triangular distribution. And if we increase the size of items in a sample to 10, we see that we have a nice normal distribution now. If we increase the number of items in a sample to 30, and furthermore, in fact, we have number of items in the sample as 80, you see that the width of the sampling distribution has actually become very narrow, and most of the sample means would be very close to the actual population parameter that we are trying to estimate. So the gist of this then is that if you want to have smaller standard error so that we have more confidence that all the sample means are actually closer to the population parameter, one thing we can do is we can take a larger sample in which we have more number of observations per sample. In that case, the standard error would be less and most of the sample means would be very close to the true population mean that we are trying to estimate. So now we are interested in talking of a practical problem that we've seen a sampling distribution, but that is a theoretical idea. For that we have to take infinite number of samples, we have to take infinite number of sample means and then draw them up, and we've seen that this follows a normal probability distribution. But usually we don't take infinite number of samples. What we can usually do is that we can only take one sample. So taking infinite number of samples is actually even worse than measuring the entire population. So what we want is, with just one sample, what can we say about the population parameter with confidence? So we're going to study that just now. For this, we have to consider some important aspects of sampling. The first thing is, जो हमने central limit theorem की बात की थी कि our assumption that our sampling distribution would be approximately normally distributed. That assumption is only true when you have large number of items in a sample, or in cases when you have n, the small n, greater than 30, 40 or even larger. फिर हम कह सकते हैं कि हमारी sampling distribution normally distributed है. Again, just for reiteration, because this can be a subtle concept, sampling distribution क्या है कि how is the sample mean distributed around the true population parameter. But in many cases, the number of items or observation that we have in a sample is actually less than the number of items that we want in a sample to make it normally distributed. तो उस केस में हम क्या करें? Because we need to approximate, even the standard error has to be approximated from the sample in many cases. क्योंकि कुछ केसेस में आपको पता होगा कि पॉपुलेशन की स्टैंडर्ड डिविएशन क्या है, आपको ये पता है और आप पॉपुलेशन का मीन डिटरमिन करना चाह रहे हैं. इवन दिस सीम्स टू बी अ लिटिल कॉन्ट्राइव्ड, क्योंकि यूजुअली वी डोंट नो द पॉपुलेशन स्टैंडर्ड डिविएशन. अगर स्टैंडर्ड डिविएशन पता है तो मे बी यू वुड नो द पॉपुलेशन मीन एज वेल. बट assuming that we know the population standard deviation, उसको इस्तेमाल करके हम standard error इस्तेमाल calculate करते हैं. But in many cases we don't know the value of sigma. So what can we do? We can actually use the sample variance as a point estimator for the population variance. And that is where the need of having a large sample is very important, because for smaller samples, sample ki variance is not a good approximation of population's variance. So to understand this, let us see this table and try to understand what we shall be assuming in case of different sizes of the sample. If the sample is large, and typically we say large is, it means more than 30, but it also depends on the kind of parent distribution that you have. जो आपकी population की distribution है, आमतौर पे उसके terms में हम define करते हैं, but typically this is taken to be 30, but you may also consider larger values. If you have a large sample, then you are okay in assuming that your sampling distribution would be normal. और जिस केस में आपको population की standard deviation given होगी, sigma given है, तो हम उसको इस्तेमाल करके standard error निकालेंगे as sigma over under root of n. But in some cases you have a large sample, but you do not know the population standard deviation. उस केस में हम standard error निकालेंगे as s over under root of n. In other cases, when you have small samples, तो उस केस में we actually do not always use the normal distribution. We use a close cousin of the normal distribution, which is actually a little more wider than the normal distribution. चूँकि smaller samples में आप एक तो अक्सर assumption कर रहे होते हैं about the population's variance. अगर हम sample variance से हम population variance estimate कर रहे हैं, तो ये estimate आमतौर पे इतना अच्छा नहीं होता, तो we need to correct it. तो उसके लिए हम sampling distribution assume करेंगे belongs to a family of t distribution. उसके अलावा if you have a small sample, you can only assume that your sampling distribution is going to be a t distribution if your parent population was normally distributed, जिससे आप samples निकाल रहे हैं. लेकिन if we do not know anything about the parent population, then we actually cannot use the methods that we are developing here, because if you don't know the parent population, if your sample size is small and the population variance is unknown, you can actually not use these methods. So we should always remember this table when we are trying to see the method in which we should be calculating our standard error, and from there our confidence intervals. और confidence intervals के बारे में हम एक dedicated session करेंगे, but for now I'm just going to give you an intuition of how it works. So before that, I need to describe sampling distribution and the relative proportion of sample means which will fall close to the sample mean. तो इस केस में sampling distribution centered होती है sample mean पे, और ये sample mean असल में true population parameter ही है. तो sampling distribution अगर आप overall देखें, उसका center जो है वो mu होता है, which is the population parameter. And most of the sample means are actually going to come very close to this center. In fact, you would observe that 68% approximately of sample means are going to be within plus minus one standard error of the sampling distribution. Why standard error? Because ये जो हमने normal distribution की पहले हमने empirical rule की बात की थी, उसके अंदर हम बात कर रहे थे कि one standard deviation of the mean. The same concept applies here, except the mean here is mu and the standard deviation is the standard error. So 68% of sample means would be within one standard error of the population mean. उसके अलावा 95% would be within 1.96 plus minus standard errors of the population parameter. और 99% जो आपकी sample means हैं, they would be within 2.576 plus minus standard errors of the true population parameter. तो इसको understand करने के लिए I'll give you an example. So we want to, given one sample, we have a sample mean. इस sample mean से मैं true population mean को estimate करना चाह रहा हूँ, पर मुझे अभी फ़िलहाल नहीं पता कि कितना मैं confidence मुझे होना चाहिए. तो उसके लिए मैं sample mean के इर्द गिर्द एक interval बनाऊंगा, और इस interval की width जो है एक साइड पे उसको हम margin of error कहते हैं, और ये basically multiple होता है standard error का. अगर आपकी sampling distribution का standard error कम है तो आपका margin of error भी कम होगा. अगर आपकी standard जो आपकी सैम्पलिंग डिस्ट्रीब्यूशन है उसका स्टैंडर्ड एरर ज़्यादा है तो मार्जिन ऑफ एरर भी ज़्यादा होगा. तो इसको हम आमतौर पे इस तरह कंस्ट्रक्ट करते हैं that the margin of error would be 1.96 of standard error if we want 95% confidence. तो फिर उस वक्त हम कहेंगे कि the interval would contain the true population parameter is from the sample mean plus minus 1.96 standard errors. तो इस केस में सबसे पहले, as can be seen in the slide, we are observing that the first sample mean is very close to the true population mean. उसका इंटरवल उसके इर्द गिर्द हमने बनाया दोनों साइड पे 1.96 SE, और इस इंटरवल में for the first sample the true population parameter is contained in this. Second के अंदर भी contained है, third के अंदर भी contained है, but for the fourth parameter we see that your sample mean is so extreme कि उसके इर्द गिर्द जब हमने इंटरवल बनाया है it does not contain the true population parameter. And this is actually indicative of how confidence intervals work. Approximately 19 out of 20 times you would actually have the population parameter inside your interval. But on average, in the long run, you are going to miss the true population parameter in your interval approximately every 20th time. This is obviously an approximation. We must understand that we cannot state here that the population parameter is within this interval with probability of 0.95. That is not possible. We cannot state that in classical probability, जिसको हम frequentist approach कहते हैं, because the population mean is actually a fixed quantity, or it is either inside the interval or it's not inside the interval. We're interested in constructing intervals, और before we've constructed the intervals हम ये claim कर सकते हैं कि if we construct lots of intervals then 95% of those intervals would contain the true population mean. तो इस केस में आप देख रहे हैं कि बाकी samples के लिए means they are close to the population mean, and most of the time the interval is going to contain the true population mean. In the long run we can say that 19 out of 20 interval estimates will contain the true parameter. इसको हम extrapolate करें, this becomes 95 out of 100 interval estimates will contain the true parameter. We can also extend this idea for more confidence. If we need more confidence, we need to cover a larger range, क्योंकि sample mean can occur on both sides of the true population mean, and if we want to have more confidence, then we should be covering a larger interval, and that is actually the case when we want to have 99% confidence. जो margin of error है, that's calculated to be 2.56 standard errors. Again, for the case of our example, we're assuming a large sample. For the cases of small samples, हम उसको we would discuss this in a future lecture. So let's just wrap up this lecture by seeing this animation. You see that most of the sample means here and the interval around that would contain the true population parameter. This is because of the reason that we have now a wider margin of error. आपका interval भी ज़्यादा wide हो गया. So because your interval is wider, the chances of the interval containing the true parameter is going to increase. And as we can see here, in this case we are actually not missing the true parameter in any of the displayed intervals, but in the long run, before constructing the interval, we can think of in the long-term average would be 99 out of 100 intervals would contain the true population parameter, and 1 out of 100 will miss the true parameter. So I will conclude this lecture now by making two remarks. The first remark I'd like to make is sampling is fundamental to inferential statistics and therefore fundamental to network performance evaluation studies, which is scientific in nature. Because we need to make induction based on particular observations, it is important that we understand sampling, and we also give measures in the reports that we give of not only the value that we are getting from our sample, but we should also state what confidence that we have that this sample mean, as an example, is a good indicator of the population we are trying to represent. Also, we've seen that we can represent or we can estimate true population parameters from just a small sample, and that is the beauty of sampling. But we must take care to ensure that our sample is not biased, because that can then give us misleading results. With this, I wrap up this discussion. I'll see you next time, inshallah. Assalamu alaikum.